Hey everyone, this is video 4 for Unit 2. We are going to wrap up coloring our periodic table tonight, and we're also going to talk about orbitals, and I'll have you guys do some practice with the 2n squared equation that we've been talking about in class. So at this juncture, you should have your periods labeled on the left-hand side of your periodic table, 1 through 7. You should have your groups labeled 1 through 8 across the top, not including the transition metals in the middle. You should have colored column 1, family 1. You should have colored family 2, family 3, and 4, 5, 6, 7, and 8. And those should be in a key at the bottom of your periodic table. You should also have colored in the transition metals right here. And you should have them labeled the alkali metals for column 1, the alkaline earth metals for column 2, boron family for column 3, carbon family, column 4, nitrogen family, column 5, oxygen family, column 6, the halogen group, column 7, and the noble gases or inert gases for column 8. So for tonight, we're going to pick up with the rare earth metals. These are called the pull-out elements that we talked about in the very first video. So you may have colored in these two groups. If you did, that's okay. If you did not, thanks for listening. And these are the rare earth metals. So at this point, we are going to label these two groups at the bottom here. In your notebook on the right-hand side, remember that you're recording the notes. And on the left-hand side, you're recording any questions you have, any ideas that you have for things you might want to do for a homework assignment, any brainstorming you have, anything you want to ask me in class, that's going on the left. And the blue information that I'm giving you as notes is going on the right. So this first row, this is actually a continuation of row 6. That is called the lanthanide series. It is called the lanthanide series because it starts off with lanthanium, which is the first element right here. And these groups are generally radioactive, so most of the pull-out rare earth metals are radioactive. They're usually silver, gray, silvery white, and they're very electric and they're very reactive. The ones underneath the lanthanides right here, these are called the actinide series because it starts off with actinium and they go all the way up to 103. So in some periodic tables, the pull-out elements come from the second column here, and in some periodic tables, they start with this metalloid column here. So on your periodic table, they have pulled them out of column 3B, the first column of the transition metals. So they would actually be right after barium and radium, respectively, and that's where we pull them out. So again, just in case you forgot, these are pulled out because most of them are synthetic, meaning man-made in a lab. They're not found naturally in the environment. There are a couple that are, but most of them are not. And because of that, most of them are radioactive. They're pulled out for that reason, in addition to the fact that if they were in the periodic table, they would kind of throw off the pattern that the periodic table currently has, which is a very nice pattern. All right. So, quick review. We've covered how to find atomic number. That is the proton count of each atom. That is very specific. It is the characteristic of that atom. It's sort of their fingerprint that tells them what atom they are. And by adding or subtracting a proton, you completely change the atom. So in a lot of classes, we talked about going from helium element 2, which is a clear gas, and adding one proton to it and creating lithium, which is an explosive silver metal. So just changing that one little proton completely changes the substance. So don't forget about that. We also talked about atomic symbol. Those are the 1 to 2 letter sort of nickname symbols that we use to identify the atoms. They're usually from a Latin name. So things like C for carbon, N for nitrogen, O for oxygen. We also talked about the relative atomic mass, or the atomic weight, which for our atoms actually tell us how many subatomic particles are in the nucleus, being the protons and the neutrons. And we talked about why the electrons aren't counted in that number. They're very, very, very small. Some are more than a millionth smaller than your average proton size. They're also really far away from the nucleus. They're also whizzing around super fast, not in one space long enough to obtain a mass count. We talked about the fact that each orbital level can only hold a certain number of electrons. We talked about the valence electrons being the outermost electrons, the only piece of the atom that is involved in chemical bonding. And we reviewed the formula 2n squared, where n is the number of the shell. So if you want to figure out how many electrons go in shell 1, shell 2, shell 3, all the way down to shell 7, you would just plug in the number of the shell that you're on into this equation. So for example, if we wanted to know how many electrons could fit in shell 1, we would put a 1 in right here for n, and it would be 1 times 1, or 1 squared, which is 1, times the 2, the coefficient, which would give us 2. So now we know that there are 2 electrons that can fit in shell 1. Okay, so we are going to practice with this a little bit. I know we did some in class, but I wanted to give you a chance to practice on your own. So all of these examples are going to go on the left in your notebook. And again, you will need your periodic table, so even though you're done coloring, hopefully you still have it in front of you. And I'm going to just go through. What you should do is pause it when you see the example. So like after I'm done talking, you would pause it on this slide. And then what I'll do is I'll load up a picture of what you should have drawn so you can double check and make sure you did it right. And then if you have any questions about the atom that you drew and what you may have gotten incorrect, you can ask in class, and we can do any of these examples that people need to review in class. Okay, so the first one is neon, atomic symbol Ne. I just named it for you. So you are now going to do the number of shells that this element has and the number of valence electrons that this element has. You can draw it with just P and N in the nucleus to symbolize protons and neutrons in the nucleus if you feel comfortable doing that, or you can draw out all the little circles with the positive signs inside of them like we do in class. So pause this, take a minute, draw neon, and when you're ready, unpause it, and I will click on the next slide for you. So if you're correcting your neon, you should have known the name was neon because I just told you. And you should have gotten that it has 2 periods. Two shells. It's in period 2. And that it has 8 valence electrons. It's in the 8th group. So neon is one of our noble gases, and it is non-reactive. Next example. This is a tricky element. Sometimes seems to be the easiest one, but it's actually not. So go ahead and pause that one. And hopefully when you unpause, you figured out that's hydrogen. It's in the first period, so only 1 shell. It's also in the first group, so only 1 valence electron. And you may have drawn hydrogen with no neutrons, and that is possible. It is possible for hydrogen to have 1 proton and no neutrons. It has a different name if that's the case. It's also possible for hydrogen to have 1 proton and 2 neutrons, and 1 proton and 1 neutron. So there are 3 naturally occurring forms of hydrogen. And they each have a different name. Extra credit if you look up the 3 different versions of hydrogen and show it to me tomorrow. Example 3. Answer for number 3, this is beryllium. It's in period 2, so 2 shells. Second group should have 2 valence electrons. Example 4. And answer for number 4 should be sulfur. Third period, 3 shells. Sixth group, 6 valence electrons. And you know in class I draw these paired up, so I would start 1 here, 2 at 3 o'clock, 3, 4, and then I'd go around and pair up 5, pair up 6. So that would tell me how many extra bonds that sulfur can make. All right, so 10 minutes, that's it. We're all done. I will see you guys tomorrow. Thank you.